Consteel is, I think, a very powerful analysis design engine. Mastan is a little bit different perspective. It's a very good teaching tool and very good at allowing you to run nonlinear analyses and essentially do simulation type work. Fairly simple simulations using either first order, second order elastic analysis or second order analysis with a plastic hinge model, so you can start to get a handle on the ultimate capacity and how things work for that on a framing system. We can plot some load deflection curves, other types of curves to understand what's happening in terms of the nonlinear behavior as we increase load on a structure, whereas Consteel isn't really set up for those sorts of studies. It's more set up to accomplish designs. And I'll try to relate the two a little bit further as we go along. I put in this slide that was from the previous topic at the front here, just to so we can remind ourselves what is the frame that we're studying. And so it's a 5-bay modular frame. We've got exterior columns that are wide flange sections, 310 by 97. Everything is grade 345 steel. The interior columns are hollow structural steel sections, so relatively light. We're modeling those as basically pin to pin, or modeling them as leaning columns in our analysis of the system. So our beam spans are 12.19 meters. The story height is 6.096. So these are basically converted directly from imperial units that the frame was originally worked in. And you can see the dead snow and wind loadings, idealizations on the frame. And we're going to focus mainly on looking at load combination 1, but there's some slides that are hidden, but you would have in your materials in the PDF that also show load combination 2. Again, in terms of the design, the columns are braced at top and bottom out of plane, but it's a moment frame, free to side sway in the plane of the frame, and our lateral load resisting system is the girder and the exterior columns. All the interior columns aren't helping. In fact, they're tending to destabilize the system. And lastly, in terms of the girder design, we've got bracing at close intervals to whatever extent we need. You can assume that they're all at 1.524 meters, that's 5 feet. This is a typical practice in the US. But we would take out flange diagonals in some places where they're really not required in a subsequent step. So that's the frame we want to study. And so what I'd like to do is we'll bring up Mastan, and I'll basically show you a few things where we work this model. Is just to save time, I want to bring up the model that that I've just uploaded to the Google Drive, and we'll work from that rather than creating the model from scratch. And so I'm starting up the program. All right. So let me go and find the file on my system here. So it's under modular frame there on the Google Drive. Just make sure you've found it. And I'm going to run the one that says second order inelastic. I made a number of tweaks there to the model relative to the other models that were there. So just a few words about Mastan itself as a software program. The range of capabilities in Mastan are relatively small. It's not a design program. It's all set up to really facilitate doing nonlinear analysis of frames and making that as easy as possible. You get to where you need to do a design, okay, well, good luck. If you wanted to try to use Mass10 for design, you can only create one load combination and analyze that. You'd have to create another model for the next one, and the next one, it's not set up to do design. Nor are there any code checks in Mass10. But in terms of the menus, fairly typical menus across the top of the screen. You've got things for file management. You've got things to manage the view on the screen. Geometry. This is more of a traditional software system where if we're building our model, we have to define nodes, and then we have to define elements and their connectivity to all the nodes. So in Mass10 you do that graphically. There is some automation there that's available in the system, but most of the time we would use Mass10 for fairly simple structures, and you would essentially create your nodes, put all your elements in that you want to represent the members by, and you're off and running. And so that's geometry. And there's capabilities in geometry to put in releases. So here I've already defined this frame. I started out and defined the frame just by defining all the nodes at the top and bottom of all the columns, and then putting elements in between all those locations to represent the column and the roof girder members. And then under geometry, I can go to define connections and flexure, and here I can select, let's say I select this column here. I have to figure out which is the start and which is the end. I had put in my elements from top to bottom, so the bottom's the start, the top is the end, and so I would need to say, okay, the end is pinned. I've already defined that here, but I can hit apply, and okay, it would insert a pin or release in terms of the moment at that particular node in that member. So that's, in that way, we have leaning columns modeled for all the interior columns here. The bottoms of the columns, I'm defining displacement constraints X and Y, and I'm not restraining rotation. So that's automatically basically got rotation free at the base. I could put in a base fixity and then put in a rotational spring if I want to. Mass10 has that capability if I want to do a model that has that. And once I had all those pieces in, I subdivided the roof girders in each bay into two elements. The main reason for that, we're going to use a plastic hinge model, and the loadings we're going to use are such that we don't form plastic hinges within the span. But if I had a load combination that did, Mass10 only models plastic hinges at element ends. So I have to be sure to put at least a node in the middle of a span, and that would at least give me an approximation of forming a plastic hinge. If the maximum moment actually is slightly off of that, well, we're missing it a little bit. But we would have a reasonable approximation with plastic hinge forming at the middle of the spans in a typical solution if we had plastic hinge forming within the length. Now, also when I define the model here, we can do a check. If I go to information on the nodes, I can click on a node here, and it tells me the nodal coordinates. And so it's telling me 12.192. So if you do 0.002 of 6,096 millimeters, that's basically the delta naught. So I've defined my nodes at the top with an initial out of plumbness. I don't have to do that. I could define the perfect geometry to start, and then there's an option in Mass10 to move the nodes, move them manually. There's also an option where you can get a buckling mode and then say, oh, I want to use that buckling mode and I want to displace the nodes by some multiple of the displacements that are in the buckling mode. An important aspect in Mastan, again, part of the attributes of Mastan where it's just a very simple package, it doesn't have the capabilities that most professional programs have of, oh, let me put in my loads or my geometry in whatever dimensions I want. So everything has to be consistent units. And so I'm doing everything here consistent units of kilonewtons and millimeters on everything. Okay, which silly mistake for someone that doesn't use SI a lot. The main thing I had to fix with the inelastic file I just uploaded is and my yield stress needed to be 0.345 kilonewtons per millimeter squared. All right, I think that covers those. So once you have geometry, you can define properties of the system. And for the properties, you can basically go to define section and you can access a database that's the American Institute of Steel Construction database, and that is also in SI units. So the AISC database in SI, and so that's how I've uploaded the cross sections that I showed you from the PowerPoint a minute ago. So then once we have sections uploaded, we can attach sections. So I can select whatever sections I've chosen. So I've got 3 different sections here. I can click on members here in the system and attach cross sections to different elements in the frame. Mastan doesn't know members, it only knows elements, so I have to do everything's element by element here. Whereas in Consteel, we were just doing everything in the context of a member. They could span over multiple support points or what have you. The material, so we can define a material. So I've already done that. If I want to modify the material, I'll just do that because that allows me to bring up the material and basically show you what we have here. So notice I have E equals 160. That's because we're running this frame as a direct analysis model. So we're using a stiffness reduction of 0.8 on all elastic stiffness contributions. And also notice for FY, I don't have 345. I have 0.9 of 345 because the factored plastic moment resistance is 0.9 MP. So I won't be using 0.9 MP in my plastic hinge model, or 0.9 of the yield load if we're talking about axial. And then lastly, last few things with the Mastan models, we can define fixities. And so I basically clicked X, Y, you select nodes, and so any nodes you get, you can apply, and that's how I applied my boundary conditions, X, Y constraints at the base. Now notice what we did in Consteel. We spent a fair amount of time defining all the out-of-plane bracing. Because in Consteel, it's just like in a physical structure, it's always a 3-dimensional structure. Of course, there's advantages to that. And in Consteel, we've got relatively better graphics. Here, everything's just a stick model in Mastan. So I think there's definitely value there, but in terms of being simple and quick, if I really want to do a planar analysis, I can tell Mastan, hey, this is a planar analysis, and I don't have to bother with any degrees of freedom out of plane. So that's what we're doing here. So those are the constraints. If I had any concentrated loads, I could apply those by defined forces. I defined uniform loads to get the uniform load that we have on the roof girder on the frame. And so that pretty much completes all the model. So now let's do a few things with this. I wanted to spend more time. I didn't want to take too much time to walk through the model creation. I think that's fairly straightforward and relatively easy to do if you're familiar with matrix structural analysis. Let's do a few different analyses here in MASTAN. MASTAN actually has some modal and also dynamic time history analysis capabilities. We're not going to go there, but we're going to focus on static analysis capabilities. Let's just start with a first order elastic analysis. If you're building a model and you're going to do some sort of a nonlinear simulation, of course you always want to start simple. Say, okay, is this thing working first order elastic? And so let's pull that up. You can see it's planar frame, and I can apply, and faster than I can snap my fingers, I have the analysis result. And so I can go to the results, and we get various diagrams. One of the so-called diagrams is the deflected shape, and I guess you can see that a little bit there. The dark blue isn't the best on a black, but yeah, there's the deflected shape of the structure. You say, okay, yeah, that looks right. We can look at some other diagrams such as either axial force, or let's just pull up. Now in MASTAN, the convention in MASTAN, to just make everything confusing, so in the AISC design manuals, MX is always major axis bending, MY is minor axis bending. For MASTAN, MZ is major axis bending, MY is minor axis bending.
But that's the ISA.
Okay, good. Yeah, so, and of course, I don't think they were doing it to be consistent in that way. I think Professor McGuire liked the aspect that X was the longitudinal axis of the element. So he didn't want to be calling MX the major axis of bending. So if we do MZ here, everything is, by default, is such that the web is in the plane here when we defined the model. If I wanted to do weak axis bending, there's a capability to rotate the element by 90 degrees, so it would be weak axis bending. So if I apply, just know I can see this, and I may want to do things like, for example, go to labels, and I can turn off maybe I'll leave the node and element numbers on for now, but I could turn off the loads, and it makes it a little bit easier to read moment values. It basically shows moment values at all the nodes. But now let's, in terms of thinking, okay, we want to kind of understand load deflection behavior of this frame. Let's use another feature of MASTAN. And you know, it's I won't try to apologize for MASTAN, but the graphing capability could be better, but it works. It's stable, and we'll use it to glean some information here. So what you can do, from results, I just pulled up an MSA plot. So basically allows us to do an X versus Y plot of anything we want in the model. So this was from results, and then clicking on MSA plot. And what I want to do is, so I have to kind of click through and define, well, what do I want to do for the x-axis of the plot, how about the y, and so forth. So I'm going to click on x, and then down here under what do I want to do for the x, I'm going to click on here, displacement. And so now, unfortunately, in MASTAN, I have to figure out, well, what node do I want, and remember, and see what node number. I'm going to do node 10, which is close to the middle of the frame. So node 10, and I want to go do displacement in the lateral direction, x, with a scale factor of 1 over the story height. Let's see if I wrote that down. Oh, I did. Okay. So that's 1 over 6096. And so that way we're going to plot drift ratio. So that's 0.000164044. 404. Okay, so apply that. And then on the vertical axis, so define Y data. So there, a convenient thing to use for plotting a lot of times is, so we defined a loading on this frame. The loading happens to be all the loads for load combination 1, which was dead plus snow load here on this frame. And so the so-called applied load ratio, when we work with that, that's basically, well, how much of that factored load have you applied? If you applied 1.0 of it, you've applied the full load. But if I want to say, well, can this frame withstand larger load than the design load that we're trying to check? Okay, I can look at applied load ratios larger than 1. How far can it go? All right. So the applied load ratio is a fraction or a multiple of the load that we've defined on the structure. So I'm going to click on that for the y-axis, and then we can go back to curves again, and we can say generate curves. So I've run an analysis. It's got the results from this first order elastic analysis that I've just done, and so I'll tell it here, give it a label here of first order elastic, and I'll take the default properties of the curve here, hit apply. Oops. Okay, what did I do wrong? I think I know what I did wrong. Okay. Let me erase that curve, and I'm going to go back. What I did wrong is I selected applied load ratio, but I never applied it. Okay, so I didn't have anything on my y-axis still. So now if I generate curves now, I think it should work. I'll do 1 ST for first order elastic, and that's better. Okay, all right, now that's not too exciting. It's just a line between 2 points. But what I want to do next is let's come back to the main program, and let's go into static second order elastic. Okay, so here we have various options. And this page allows me to say a little bit about what are we doing and what were we just doing in Constio versus what are we doing here. So Professor Pradeep was asking me about this the other day. There is capabilities to do things that we say or what we call RICS analysis. It allows you to follow a load displacement curve through a limit point and an iterative solution. Mass10 has that. We're going to use it typically, if I just needed to get results for a design, I would actually set this up the way Constio was doing it. And that was simply, well, the nonlinearity in most of these frames is minor enough to where I can apply the entire load that I want to apply, and then I iterate to convergence. And so I was going to use the board for a few things today. And so if I plot a displacement versus a load, just as a representative generic load, generic displacement, and a second order elastic curve, we may have a response like this. So what we're doing, if this is the load level that's our design load level that we want to apply, what we were just doing in Constio is we're starting at 0, we're getting a tangent stiffness, which basically is the linear elastic stiffness of the system at 0 load. It steps linearly to there, so you do a linear solution, but now you evaluate, okay, I have these externally applied loads at the nodes within the finite element model. The elements are resisting the displacements by internal forces. This is the applied load, but this is the internal force at that displacement. And then we say, okay, well, we don't have equilibrium between external load and internal force. We're going to iterate this. We're going to build a tangent stiffness now based on the current state of the structure at this iterative step. We step to try to basically result. This is basically a Newton-Raphson root finding algorithm, but on a matrix of all our nodal displacement quantities within the structural model. We get to here, oh, we still have an unbalance. So we keep iterating until that unbalance is negligible. Okay? So that's the process that we're using in Consteel. And so you basically say, well, run the load, oh, let me get the results. So it just says, oh, well, here's your results. It's what's going on right there. Okay? Now, I could do that here in Mastan by running load control and saying if I want to just apply the design load, an increment of 1, I just want 1 increment. The maximum applied load ratio would be 1. I'll rip, and it's going to come right back for most civil engineering frames. And okay, I've got my result at that load. But in terms of looking at behavior, was there a question? In terms of looking at behavior, we want to understand, well, what's this nonlinear load deflection curve like? How's it working? So that's what we're going to set up to do here. So I'm basically set up to increment at 10% of the load here. Load control, there's other options, but load control is basically this Newton-Raphson algorithm. I'm going to tell it, okay, if I get to 14 increments, I want it to stop because I don't want it to just keep going forever. And I have a maximum applied load ratio of 1.4. And so at that, I want to go make sure this is start new. I'll explain what the other option is there in a minute. And we hit apply. Okay, and now it didn't actually go to 1.4. The reason is Mastan has some heuristics that aren't very well explained, where it will vary the increment size a bit based on the nonlinearity in the structure. And so it didn't get to 1.4 with 10 increments or 14 increments of 0.1. It got to 1.259. So we'll just take that as a representative solution. So I could look at things here. I could see another plot of my deflected shape again. You can see that's quite a bit more now because of second order amplification. I can scale that back to 10 times to make it look a little more reasonable. Well, even that's not very reasonable. Let's go 5 times. And I can go to view and say fit what's on the display, so I've got everything there on the display. Okay? But now let's go back to MSA plot. So I can click down here and pull up MSA plot again. And I can tell it, okay, I want to do a second, it's ready to do a second curve. So this is my second order elastic response. And we'll use a different curve. I'll use a green curve here, dashed, to kind of make it so we can distinguish it a little bit better. And we'll apply. Oh, it looks like things are starting to get bad here. That our displacement is starting to get relatively large compared to that elastic solution as we've gone beyond the applied load the load that we wanted to apply on the frame. Okay, and so now relating to that, so notice it's kind of leveling out it looks like it's starting to go fairly horizontal here at about 1.26. If we come back to Mastan, and if we go to analysis, and I can do an eigenvalue buckling solution, elastic critical load. So if I run that, comparable to what we were looking at with elastic buckling in Consteel, and if we go to results and plot the deflected shape for that, it will, okay, I need to scale this up now. It's not quite as nice as Consteel, where Consteel figures out what it needs to do for displaying for scaling the graphics. Come on, okay, we're getting closer. So 2,000 times, okay, that's a bit, oh, that doesn't look right. That's weird. Okay, I am not going to try to figure that one out. That's weird, okay. All right, that's a weirdness here. The buckling load looks about right, but something is weird with the displacement there at the middle. You can see the eigenvalue buckling load is 1.27, so you can see that, oh, that's why it's essentially the displacement is starting to become very large. We're getting close to the elastic buckling load on the frame there. Now this is an elastic buckling load based on a reduced stiffness of 0.8 of the elastic stiffness on the system. So the actual elastic buckling load would be 1 over 0.8 of that with a nominal stiffness. Okay, so now from here, wasn't doing that earlier. There is a first order inelastic that's more akin to a traditional plastic design type solution without considering second order effects. I'm not going to go there. I want to use second order inelastic to kind of explore the collapse behavior here of the frame. And we're going to use a solution type. Mastan for nonlinear plastic hinge analysis solutions does not have an iterative, an incremental iterative capability. Everything is only incremental. And it does have something that's called predictor corrector, which within each increment you step for that increment. What predictor corrector does is it figures out the tangent stiffness associated with the state of the structure at the middle of that increment, and then goes back and steps with what it found as the tangent properties at the middle of that increment. So it makes the for a little better accuracy with a coarse increment size. So I'm going to step using predictor corrector with a 0.05 increment size, 0.05 of the design load that we're working with. Now so let's say, okay, we'll go as many as 30 increments, and if I get to a load ratio of 2, I want to stop. So here I notice I've got continue previous. We'll come back to that in a minute. You always, if you have that there, you always want to start out with start new. Okay, so with all those settings here, we can hit apply, and it starts running. It got to increment 24. Now what Mastan does is it starts incrementing, and then if in an increment it detects that a plastic hinge is going to form somewhere in the structure, so I've reached a load level. It's going to form a plastic hinge. Let me trim my increment back so I just get to the start of that plastic hinge formation. And I'll get everything set at that load level. Now I have a plastic hinge at this particular location. Now incrementing out, I found another plastic hinge. Let me scale back to where that plastic hinge starts. And so the incremental scheme actually works rather well in a large structure where you've got a lot of progressive plastic hinge formation. The plastic hinge formation itself will happen at fairly small load increments as we start loading the structure up toward collapse. So that's what's happening here. And at increment 24, it detected a limit load, which basically means it formed its tangent stiffness again, wanted to apply some more load, and it found I can't apply any more load. The structure can't take any more load. And in that sense, what you could say that we're doing here is it's going to stop and say, okay, I've got my load capacity now, but I can continue from that, where in essence it's going to go into a mode where it's going to take away the load as it's going into post-collapse. So it would be akin to what you would do in the lab if you were doing an experiment in displacement control, and you've reached the failure load of the structure, and you're holding at this displacement, and you say, okay, well, let's push it again. You give it another displacement, and you say, okay, well, now at what load is the structure is pushing back with less force? I've reached the collapse load then. I'll give it some more displacement, and so the structure keeps pushing back with less and less force as we give it more and more displacement. So that's, in essence, what's happening here with this system. So this is where I'm going to use continue previous. So I could expect things here, and actually let's do that before we go further. If I go to results, if I do deflected shape, and I better scale my increment back. I don't know what was going on with the eigenvalue buckling solution. That was a bit strange. Let's do a scale factor of 10. Okay, so those yellow triangles that have come up, those are basically saying we've formed plastic hinges at the ends of those elements. And it tells me when I formed a plastic hinge in the roof girder that's continuous over the top of the leftmost interior column at 1.129 of the factored loading that we wanted to design this frame for. And then I formed a plastic hinge at the column, the exterior column on the right. I'll probably refer that to that as the leeward column. We don't have a wind load here, but we had a out of plumbness to the right on the structure. That's why the structure is tending to sway to the right. It's a symmetrical structure, symmetrically loaded, so without the out of plumbness, it would we wouldn't have any lateral displacement. Okay. So I might call that a leeward column, if you wish. And so at 1.157, we form a plastic hinge there. And what's happened is that at this point, the model is basically detecting it can't take any more load once we form these two sets of plastic hinges. But I can continue from here. If I go back to the inelastic analysis, so continue previous, and if I hit apply, sometimes I might want to step at smaller increments once I get into post-peak, but we're okay here. I'll keep it going at 0.05, and I basically I'm at 24, so it going to increment 6 more increments before it then stops at 30. Okay? So now, let's go back to MSA plot to understand what we have there. So if we pull up MSA plot, and if I plot the third curve here, second order inelastic, and we'll give that a cayenne and dotted, and we'll make it a heavy dotted curve. Oh, so now the green dash curve, that was our second order elastic analysis. Okay? And what you can glean from this is it looks like it's not perfect. If we kind of zoom in there, the dotted curve is a little bit off of the green dash curve, but it's reasonably close. It's a pretty good solution. It was a little high there, and then we actually formed started to form our first plastic hinge here. So now that we've lost stiffness, we formed the second plastic hinge. Now from this point on, the structure can't take any more load. If we push it with more displacement, it's pushing back with less load. Okay, so that's our load displacement response in terms of load versus drift ratio. And if I wanted to clean this up, we could go to X attributes and set, let's see, what do we have? So if you're looking at the what's in the PowerPoint that we'll come back to in a minute, so 0.04 and 4 increment for divisions, okay? And then we could do y-axis and here, oops, for the y-axis we'll do, I think we're 1.4 is what I'm showing here in a second with, I think, 7 increments apply. Okay, so that's, we're basically going to see these results in part in what I'm going to show you in a minute, and we'll walk through the behavior. Now, the second order elastic here is with a reduced stiffness. If we're using effective length method, it's with a nominal stiffness, and so it would have a bit higher second order elastic curve. Notice that because of the geometric nonlinearity, we've got larger displacement and a nonlinear low displacement response compared to what we get from just a first order elastic approximation. But when so second order elastic analysis is kind of the staple for the design, right? When we run a second order elastic analysis, the analysis is pretty stupid. It doesn't recognize anything about, did I get some elasticity forming in the structure or what have you? But with a program like Mastan, it's detecting, again, here's where we were at this point. We had the first plastic hinge form over the leftmost interior column. So that softened the structure a little bit, so it's starting to go a little bit flatter with the low deflection curve. And then the second plastic hinge here, and we've basically collapsed the structure. And if I come back to the display here, and if we look at, so it was increment 24 where things got interesting. So if we go back to increment 23, it was before that. Yes, 23 when it got interesting. So at increment 23, I don't see any plastic hinges. Then, or 22. And at 23, we formed a plastic hinge over the first interior column. Then at 24, apply. I've got a plastic hinge over over the other column. Now, when we try to take it further, it starts removing load with getting larger displacements. And so when we remove load, so Mastan detects, I took load away, so that I'm actually elastically unloading from that plastic hinge. The plastic hinge disappeared. But it's still tending to sway more, so I've still got a plastic hinge over here in the column on the left. And if we keep pushing out all the way to 30, you can see at 30, so now I'm really everything's going to go over on the floor because we've got plastic hinges at the tops of both columns. Okay. Now, lastly, I want to show you one other aspect with the top of the column over here on the right. If we come back to MSA plot, actually, the easiest thing for me to do to reset MSA plot is just to close it. And then I'll go back to results and open it again. And so what I want to do is what's called a force point trace for the moment versus the axial force at the top of the leeward column. And so for the x-axis here, I'm going to select element force, and this is element 6 over here. And so in element 6, I want the moment mz on the horizontal axis, and I want it to be at the end because the top node is the end node. I'm going to plot just the moment straight up there, so a scale of 1. So apply. And then for the y-axis, I want to do the element force, again in element 6, but P. And I'm going to use the start here because axial compression will be a positive upward at the base of that element. So that is the same axial compression at the top. And so at the start, scale of 1, apply. And so now if I did everything correctly, and if I generate the curve, okay, what's happening here? So on the horizontal axis, we're plotting moment at the top of the column. On the vertical axis, we're plotting the axial force, you can say at the top of the column, positive compression. And so we start loading the frame up, and we have this, so that the moment is increasing nonlinearly in that column until out here at this point, we actually reach what we say is a yield surface for the cross section. We've reached the point where the full plastic strength of that cross section has been used up. And so at that point, what Mastan does is it says, okay, I've inserted a plastic hinge. Now, Mastan has essentially implemented the mechanics of plasticity, which recognize, oh, you can get changes in force at the plastic hinge, but the forces, here in this case, force being moment on the horizontal axis, axial force on the vertical axis, if I'm continuing to plastically load, I have to stay on the yield surface. And so what it's doing as I start to fail the structure is that column is reaching a point, it can't take any more moment unless I reduce the axial force. So the axial force is dropping off as the moment is increasing there on that column. So that's what this curve is showing us. That's our force point trace here of the column. All right, so that's I think that's a good illustration of the sorts of capabilities that you can use Mastan for. If you haven't used this before, hopefully you find that to be informative. It can be a useful tool for this type of thing. Any questions here about what we just did with Mastan?